Good afternoon, everyone, and welcome to our webinar on how to improve your mechanical reliability using Ansys Solution. Before we proceed, please note that all participants are currently muted to ensure a smooth and focused presentation. However, we encourage you to actively participate and make the most out of the session. You can share your thoughts, questions, or comments in the chat section throughout the webinar. So today's agenda for this webinar is that we're going to understand how you can improve um, uh, your mechanical reliability, understanding your reliability challenges, mechanical reliability in your electrical system, how you can optimize your business by reducing cost through reducing the need of physical testing, reducing material and manufacturing cost, and also how reliability can predict and improve your product lifecycle. Electronic systems are found in nearly all industries, everything from aerospace, automotive to consumer electronics and healthcare. To ensure this system remains operational and perform their intended functions in a variety of environment, it is critical to product success and customer satisfaction. Companies who properly address electronic reliability concerns through simulation can meet many of the objectives stated here. Traditionally, companies have used a design, build, test, then break and fix in the design cycle. This process can be very expensive and time consuming. The design rules and best practice associated with this process may not provide the engineers with enough guidance to properly design modern cutting edge products. By using simulation, virtual prototypes can be created, tested virtually, and provide engineers with higher degree of confidence that the eventual physical testing they do run will be successful. Performance, safety, and cost are critical consideration in the design of electronic systems. Designs are required to reliably perform their intended functions in a wide variety of demanding environments. If electronic system gets too hot or have any mechanical failure, they may not be able to perform their intended functions. And in some cases, such as automotive, aerospace, and healthcare, this could put people's lives at risk. Many existing customers of Ansys benefits from reduced design, development, and material cost, reduced product development timeline, and improve project performances and reliability by moving from physical testing to virtual product testings. Engineers must address a wide variety of design requirements when designing electronic systems. This ranges from electrical, such as signal and power integrity, thermal, such as implementation of optimal cooling strategies, or mechanical consideration, including ability to withstand thermal cycling, shock vibration, and drop. Additionally, products are required to meet life requirements to make sure they meet their intended functions for at least some specified amount of time. Engineers also required to consider the effect of manufacturing, transportation, and product operation as a part of their design process. Ansys provides a range of tools and workflow solution that addresses a wide range of electronic reliability concerns. Its simulation toolset plays a key role in understanding how electronic systems operate and performs in a variety of application. And over the next couple of weeks, we are going to focus on each of these area in a separate short webinar. Our first webinar was on electrical reliability, where we have learned the discuss the electrical simulation to address concerns related to signal and power integrity, EMI and EMC. Our second webinar was conducted on thermal reliability in electronic systems, where we addressed and demonstrated how maintaining thermal integrity using Ansys IcePack. Today, we're going to focus on mechanical reliability. So, um, Mechanical reliability, so mechanical parts being the physical structure of PCB and other electronic components, are susceptible to failure due to excessive rapid shock, vibration, drop, and other environmental factors. Structural integrity is required to be maintained to help ensure electronic devices perform their intended functions. Answers have a wide variety of solutions to quickly preparing high fidelity simulations, models that can be used to assess the mechanical performance of electronic systems. I'm now going to hand this presentation over to my colleague, David Scholtz, who's going to go through some of the technical aspects of mechanical reliability and how Ansys can assist your organization to optimize your product lifecycle. So over to you now, David.
Thanks, Jubaida. So when we're assessing for mechanical reliability, there are a wide variety of complexities that we need to address and consider. Now, broadly speaking, we can sort these into three categories: the geometric complexities, the material complexities, and the physics complexities. So the first of those, the geometric complexity, mainly relates to the broad scales that we're looking at here. So we're talking about the relatively large scale of the PCB itself, or the housing in which it sits, through to the small components on that PCB, and further still to the small scales of the thickness of the individual layers of the board. In terms of materials, as you might imagine, when we have a large list of materials involved in any particular analysis, that already is a complexity in itself, even when we're working with linear elastic material behavior. When we start including more complex behaviors such as plasticity or creep or temperature dependence of those behaviors, then that further increases the complexity vastly. This is particularly evident when we need to complete analysis and assessments for fracture and fatigue cases, where small details and dependencies have a big effect on the result of the analysis. Looking at physics complexities, we also have a broad variety here. So we're looking at mechanical reliability. So of course, we're looking at structural effects that need to be considered. But we also need to consider the effects of thermal differences, of electrical differences, all within the same analysis. Some examples of the test conditions to be considered here are shock or vibration, so drop and impact testing. But we also need to consider the likes of thermal and humidity, and we'll go through some example of those later on. Across all of these complexities, Ansys provides a robust and quick solution to provide accurate models and representations of the products to then complete these assessments in a quick and reliable way. So looking at the way we model these PCBs, we also have a range of approaches available within the Ansys package. Now these range from the more simple, quick and easy approaches through to the far more detailed assessments where we can look at small features in great detail. So on the left-hand side here, you can see one of the simpler approaches, the homogenized approach or the lumped approach, where we take a relatively coarse mesh, either with or without consideration for the individual layers, and we lump the properties over the individual mesh elements. So each element could be representing many different scales or a number of different components within this PCB. And so we lump the properties over each of those elements to gain a broader assessment of the PCB as a whole rather than the individual features. If we're interested in the individual features, we can look at trace mapping. So this is where we're starting to get a bit more into the detail of the individual components. And what we can do here is we can read the ECAD data directly into Ansys, where the software can then automatically lay this ECAD data over a mesh that we have created and effectively estimate the amount of each material that is covered by each individual element. And in this way, we can, in a semi-automated approach, determine the material properties for each mesh element without having to create these manually. And you can see an example of the color map of these material mixes here. Moving on to reinforcements then, this is a new workflow that has been more recently introduced. This is very similar to trace mapping and the homogenize approach, but now we're including what we call reinforcement elements embedded within the existing mesh to represent smaller features like traces and vias. We're using beam type elements for this. And what this does is it allows us to improve the accuracy by modeling the trace elements without including a full 3D representation of that trace. Speaking of trace modeling, this is the more detailed approach you can see on the right-hand side here. And this is where we're including full three-dimensional representation of even the finest details. So here you can see how we've gone, how we provide several different approaches to cover the wide variety of complexities available here. So let's think a little bit about the component modeling. So looking at the individual components on the board. Now, the main challenge here is that we're relying on a detailed modeling of the leads and the solder and other small features. And we have two ways we can go about solving this. So the solutions provided are broadly covered by either Ansys Sherlock or Ansys Space Claim. And these are two very different approaches to the same problem, this complexity problem. Now, Ansys Sherlock approaches this in a spreadsheet type fashion, where we have a vast database of parts and components that's ever growing in size that then allows us to effectively treat the individual components as a black box, if you like, a background representation rather than including the explicit geometry each time. And this allows us then to assess reliability in a quick and optimized fashion without needing to repeat the analysis every time we use the same component. Space Claim takes a slightly different approach here. So when we're using the Space Claim approach, what we're talking about here is defeaturing. So what we can do is we can take the full detailed geometry, and in Space Claim, we can remove the features that are not consequential to the current type of analysis. So this is where it differs from one analysis to the next. But what we can do then is we can simplify the geometry, thereby simplifying the mesh. And in that way, we can increase the effectiveness of the analysis by reducing the timescales required for the solution. So some example applications are shown here now. So in the top left, you have an example of a solder reflow. Now, solder reflow is where we have the solder beads already on the board, and then we're introducing heating to this board to allow the solder to settle. We'll come on to this in more detail later, but the key here is that we're inducing warpage due to the thermal loading in the whole of the board, not just the solder. Moving on to the right then, we have a tumble test. So this is where we're looking at the dropping of the component as one example. So if you think of a mobile phone and you drop it, this is a good way to test that. So this is a broad strokes assessment of the part as a whole within a moving domain in this case. Moving on to the top right, then we have a shock and vibration test. So this is quite different. Possibly one of the more clear examples here is a seismic analysis. So where we have a seismic event, we have vibrations applied to the parts. And as you might imagine, those vibrations then induce deformations and stresses within the board. And so we can assess for that. You might imagine then that these deformations and stresses can have implications for fatigue. They might even induce fracture. And so you can see this on the bottom left here in the example of the solder beads. We can then assess for fatigue implications, and we can make assessments relating to the initiation of fracture. Moisture effects are also a concern. So we're talking here about the ingress of water particulates either before or after the solder reflow process, and we'll come on to this in more detail momentarily. And as a final example, we also have drop tests. So this is effectively a more detailed approach to the tumble test, where we're looking at the stresses induced within the board at the moment of impact. So it's a greater detail, a higher resolution approach to this kind of assessment. And all of these are available within the Ansys package. So let's come back to the solder reflow. In modern lead-free PCBs, we need to apply this reflow process. The trouble here is that the melting temperature of this lead-free solder can be in excess of 170 degrees Celsius. Now, when we're looking at this range from room temperature up to and in excess of 170 degrees, we have a lot of effects relating to the thermal expansion coefficients of the different components. And as you might imagine, with different materials, we have different expansion coefficients. And so this mismatch in the thermal expansion coefficients can result in significant stresses and deformations within the part. So we can assess for this. The solution here is provided through the thermomechanical analysis within the Ansys package, and we can complete this for any components as long as we have the material data available. In this way, we can provide an accurate prediction of the package and the board warpage due to these thermal loads. And this can then allow us to assess the stresses and identify and avoid premature failures due to the reflow process. So looking a bit more at the broad spectrum here, you can see we have a wide variety of problem time magnitudes as well. On the left-hand side, we have problem time magnitudes on the order of a year, maybe more. And this is where we're looking at so-called static or quasi-static effects, such as creep and fatigue. Toward the center, you can see we're starting to look at seconds and fractions of a second. And this is where we start looking at the drop testing that we've been talking about so far. And over to the far right, may be a little bit difficult to picture here. We're talking about thousandths, millionths of a second. So we're talking about detonations and hypervelocity impacts. And so Ansys provides for solutions over this broad variety of problem types in two solver types. We have the implicit methods, which tend to be faster for solution and give us the long-term problem time and magnitude solutions. And we have explicit solvers that very accurately address these very short time magnitude problems as well. Looking then a little bit at shock and vibration. These are very common events that cause failure in electronic systems. And as you might imagine, physical testing is expensive and time consuming. And this is especially true when we start looking at testing at the module or system level. So how can we solve this? The solution provided here is broadly categorized under 2 or 3 analysis types. So firstly, we can look at shock, where we have short duration, high pulse excitations. So we can use the explicit solvers for this, and we can then assess the deformations and the stresses developed by these loads. Similarly, we have vibrations, so random vibrations, harmonic events, the seismic events that I mentioned a moment ago. And we can assess these using implicit solvers, again, all within the Ansys package. And irrespective of which kind of loading we have here or which solver we're using, we can use these as a basis then to produce life predictions and complete fatigue assessments. Again, all within the Ansys package. Drop testing is very similar. Again, physical testing is expensive and time consuming. But what we can do is through the power of Ansys and simulation, we can bring that testing forward in the design cycle to before we've used any materials. And we can then decrease the time to market, decrease the time for different iterations, and thereby increase innovation through the design process. For example, here through the use of Ansys Dyna and the explicit solver to simulate complex behaviors, fracture, cutting, failure, buckling, and we can then assess the stresses, the deformations, and improve on the design before laying tool to material. The same is true of moisture effects. So we talked a little bit about moisture and ingress. And here we can see that we can allow for moisture concentrations and the swelling due to that. So imagine the solder reflow process we were talking about. If moisture gets into the product prior to this reflow process, then we can have failure due to delamination and due to trapped vapor pressures. You might think of this as a popcorn effect, where the small droplets of moisture expand due to the high temperatures and then cause a popcorning within the PCB. Within Ansys, we can assess for this. And so you can start seeing the coupled field analysis types that we have available here as well. Going back to fatigue and fracture, again, testing is expensive. And again, we can reduce this cost by bringing the design forward in the design life and testing through the power of analysis and simulation without needing to lay tool to material, at least early in the design process. So you can see some examples of this on the right-hand side, where we're looking at fatigue and fracture mechanics. So we have the vibration fatigue right at the top there in a PCB, and you can see here some life estimates in the contour. So we can make life estimates directly within the Ansys environment. Similarly, on the bottom left, you've seen this solder before. The contours here are showing us fatigue assessments. So then we can identify not only the fatigue life estimate, but which part is the minimum for this fatigue life so that we can make specific design changes if necessary. And then in the middle on the right, we can see an example of a more complex analysis where we're looking at arbitrary crack growth. And as you might have noticed, the mesh is changing through this process. So this illustrates another capability of Ansys where we have the mesh morphing or mesh adaptation through the analysis time steps. Now, we talked briefly about Sherlock and how this is a reliability assessment tool. Sherlock is now integrated within the Workbench environment, so we can use this in our familiar Ansys environment, or we can leverage the power of the Ansys solvers in the Sherlock environment, if that is the preference. So in this way, we can then pre-process our part within Sherlock, transfer this pre-processed model to the assembly level simulations in the Workbench or LS Dyna framework. And then the results of these can be transferred automatically back to the Sherlock environment, where we can then complete our reliability assessments using these Sherlock tools. Looking again then at the ingress of water and contaminants, or rather the protection against those. As we already know, electronic systems are very sensitive to the ingress of water and other contaminants such as dust. And yet again, physical testing can be expensive and usually comes at the end of the design cycle. So we can yet again reduce this cost and reduce the time by bringing this iteration forward in the design cycle through the power of simulation. And in this way, we can help to mitigate the water and contaminant ingress issues at multiple stages during the design process. In this way, we can iterate quickly through different designs and create an optimized design for physical testing later on, thereby reducing the costs and reducing the timescales to market. Now, I've mentioned a lot of structural applications here, but it is worth noting that the power of Ansys Fluent is also leveraged through this kind of analysis. And this hints at the multi-physics capabilities available as well, where we can leverage the capabilities of CFD, fluids analysis, electromagnetics, and structural analysis all within the same package. Looking now at a specific application then for flexible PCBs. We have this example where we have a PCB substrate and the copper traces thereon, and these need to be considered, or rather the loads, the stresses and deformations need to be considered through both the installation and the usage of this product. So we can see here how we can separate out the PCB and assess these deformations or the stresses within the PCB, as well as assessing these individually within the copper traces separate from the board as well. We can also create animations to help with the assessment and the understanding of the results. So we can see here how we're having to bend and deform the PCB. And we can then see the stresses developing throughout this process, helping us to assess which part of the process generates which of the stresses. Similarly, we can look at the plastic strains developed in the traces in the same way. And again, this effectively gives us a time history or a loading history of those developed strains. Now, these are large deformations within the structure. We're bending it quite aggressively. And so, as our more experienced users might be aware, users of any CAD or analysis software that is, when we start bending things to large degrees, we're deforming the mesh. And a deformed mesh can lead to solver failures or inaccurate results. So we have a solution for this as well. In fact, we have two. These are morphing strategies. So ways that we can morph the mesh so that it still represents the geometry without having these highly skewed and distorted mesh elements in the mesh itself. So the first is a 3D CAD to CAD approach where we're linked to the original CAD, and then we can remesh through the process if necessary. And another is effectively a simplified approach to this, using an auxiliary 2D representation, so a guide curve, if you like, to influence and inform this morphing of the mesh. And so you can see some examples here on the right-hand side where we've applied this mesh morphing to represent highly distorted geometries. You can see also an animation of this on the left-hand side now, where we've taken a board and bent it to show this distortion in the geometry, but we can still generate a quick and accurate result through this mesh morphing approach. So the features we've covered here, we're talking about the mechanical reliability as applied to electronics. And through the power of simulation and the Ansys solvers, we can help to avoid component and assembly failures due to mechanical shock and vibration, as just a few examples, a wide variety of applications. We can do this through assessing for issues such as delamination, component cracking, the popcorn effect when we're looking at the solder reflow process. This is due to the leading preprocessor and solving technologies available as part of the Ansys suite, enabling us to consider complex physics and multi-physics problems, such as drop tests in thermomechanical applications. And through the application of all of this, we can reduce the costs associated with physical testing. We can reduce the timescales, and we can therefore increase innovation and increase optimization before getting to market, all without increasing the runtime at all. In fact, decreasing the time to market.
Thank you, David. We are now going to take some questions, so please feel free to drop any questions that you have on the comment section, and we'll address them. So in the meantime, so Wild Analysis provides a range of services. Our experts engineer with 30 plus years of experience can assist you with projects through consultation, tech support, bespoke training, etc. With Wild Analysis, you're not only receiving support from experts at Ansys, but also from our dedicated and experienced teams of engineers at Wild. So if you have any businesses that requires any assistance from Wild Analysis, please get in touch with us. We can arrange some bespoke demos for you guys so you can see your product in real life scenarios using Ansys solution. Just going to give a couple of more minutes to see if any questions comes in. Okay, it looks like we don't have any questions today. Well, thank you very much for attending our webinar today on mechanical reliability. If you have any questions or concerns, again, please do not hesitate to contact us. And our next webinar is going to be on reliability multiphysics. So please keep an eye on your emails for an invitation shortly. Thank you very much for joining, and we hope to see you soon.